you can see from the slide, giving a short introduction to Tony is a rather difficult task. So I thought, okay, I'm not going to read all through all these points. They might be interesting, but maybe to shorten it off a bit. So I sat down and thought about it a little bit, and here's the 3 key points that I think are important about Tony's scientific career. Okay, so during his PhD and his postdoc and group leader position at EMBL, he was very contributing a lot to certain fields in science like microtubules, motors, spindle assembly, and asymmetric cell division. And this is still something that he really likes to focus on in the lab until today. But when he became director of the Max Planck Institute here in Dresden, he also pushed into a new field, and that was trying to identify all the key genes that are related to mitosis. And he did that together with his lab, and he did it in C. elegans and in human cells. And that being done, of course, the next question is, okay, now that we know all these genes, how do we, how do they interact, right? And how do they come from single molecules to complex systems like a spindle or like a single cell or tissues? And I guess that's something that we will hear something about today. And more recently, he was Leibniz approved by the GFG and awarded the Leibniz Prize, also called Cookie Prize. And I just checked it up in Easy Web of Knowledge, and in 2010, his papers were all cited more than 1,000 times in total. So he just reached that barrier. It's a pretty impressive number. But of course, there are more other interesting facts about Mr. Hyman that you might want to know. And first off, he's a very talented jazz player, as some of you might have experienced during beer hour or Christmas party. But besides that, he's a very ambitious sportsman, as can be seen in the picture. It's a very recent picture. It shows his new bike. He's very proud of that bike. And the reason he got that bike is because finally, with this bike, he thinks he can outcompete Ivan Baines in a high blood pressure bike race. And I'm really looking forward to that competition. And the last thing is very striking for me because personally, I think he invented these staircase conversations. And I don't know how many people here in this lab know these staircase conversations, but it's very typical for Tony. Because if you want to talk to Tony and he's coming or going to a talk or a meeting or whatever, it's a good opportunity for you to talk to him in this NTI CPG staircase. And I counted it, it's 50 steps. You basically, as a PhD student, you have to be able to present your whole data that you did in the 2 weeks in 50 steps, right? And it's really a good exercise. And in these short conversations that you have there, he's always very focused and gives you good feedback. But he also never loses his vision out of sight. And I think this is something that he will now talk about, and Tony, the stage is yours.
Well, thanks, Ollie, for that nice introduction. It's true. I'm trying to be Ivan. That's one of my main goals. My only real goal in left in life, actually. I'm worried I'm never going to reach, but I know that. And thinking about a vision talk, it's very interesting to think about what to say, because I think the idea is not to give a sort of standard seminar, but maybe to reflect a little bit on what one's done and what vision one's trying to achieve in science. I think the problem in doing science is that you have a long career. Okay, so when you're a PhD student, postdoc, those times that loom so large in your mind at that time turn out a very short percentage of the whole time you spend in the scientific career, and you have to do something in that career. And the way, of course, to do it is to have some vision of what you want to solve. But that vision is obviously going to take a long time to achieve, so you have lots of byways along the way, and you do different things, and often you just step back and think, what was the goal that we were trying to achieve, or we are trying to achieve. And I think, for my case, as with most biologists, I'm interested in the following question, which is, how does complexity arise from molecular interactions? Because the problems we're interested in, such as cells or tissues, are many orders of magnitude bigger than the molecules that they make up. And so how is it that the interaction between molecules, which are 10 to the 6, 10 to the 7 times smaller than the structures they make up, how do those molecules interact to actually make the structure we're interested in? And that's a really sort of fascinating problem. We really have very little idea at this point about how we make this link. How is it that complexity of the organism is determined from the interaction of molecules? Now, I've worked on this for almost all my career in this little coelacanth embryo. It's a fascinating system to study problems like that because it's 50 microns long, so it fits perfectly into the lens of 100x, the lens of a microscope. And you can time-lapse it very simply under a microscope and follow the events of cell division. So what I'll show you in this movie is just after fertilization, where you've got the sperm and you've got the female pronuclei. So the two haploid pronuclei are now inside the cytoplasm, but they haven't come together to form the zygote. And then you have the process of pronuclear migration, where the two pronuclei lift off, and they come together, and they're going to migrate to each other. Boom, they come together, they go to the center, and now the life of the zygote has started. And that is really what happens to every single organism at the first stage of its life. And then they undergo sets of successive stereotype cell divisions. And you can see the time down here is in minutes. So the whole movie took to about 30 minutes. And these events are very, very stereotyped. If you look at embryo after embryo after embryo, they do exactly the same thing. So John Sulston was awarded a Nobel Prize for aspects of the post-embryonic analysis of coelacanth, primarily because of its invariance. But actually, the cell biology is very invariant. So you can look at many embryos, as I've done over the years, and there's very, very little variation. Now, the fascinating thing about studying a system like that is that you're looking at the transition of cytoplasm from an oocyte to a fertilized egg. The cytoplasm of any embryo is a gift from the mother. So the mother makes this bag of cytoplasm into an oocyte. The oocyte is relatively undifferentiated in most organisms. And the sperm comes in, and the two of them together then make a fertilized egg. It's a fascinating process, of course, because the oocyte and the sperm will die unless they come together. And once they do come together, they then ensure you go on to make the next generation. And so this problem of how you make the oocyte and the fertilized egg is a problem that's fascinated me since my PhD. Now, if you want to study a problem like that today, the first thing you'll do is say, what are the genes involved in this process? In other words, you want to create the catalog. The catalog of genes required for your specific process. So you can be broad and say, I'm interested in all the genes required, say, for the oocyte to egg transition, or I might be interested in a set of genes involved in protein migration, or any one of the bits of biology you're interested in, but you'll create the catalog. So the sort of catalog you might want to create is to take the genes and try and assign a function to each one of these genes in your own particular process. But putting this together, I thought it's interesting to step back and think, why do we think that's what we want to do? Historically, how have we come to that conclusion that if you want to study a problem, the first thing you need to do is a genetic screen to try and understand the catalog of genes involved in that process? And if you go back and think about that historically, about the turn of the century, one of the key people who opened up this field was Bovary, in the late 1900s, the organization of cells. And if you read the classic works of Bovary, so the turn of the 19th to 20th century, cell biology of the type that I've always worked on was the hot field. And there are many beautiful papers with lovely microscopy describing this problem. How is the cell organized? How is the complexity of the cell put together? And they were really fascinated by this problem as well. Bovary was particularly interested in chromosomes. But other people were interested in other aspects of this problem. And then there were other people who came along, for instance, such as Alexander Oparin, and he wrote a lot on the origin of life. And he really thought more about the physical chemistry of the cytoplasm. He considered the cytoplasm as a bag of molecules, which are physical, and their organization is defined by physical-chemical principles. And one of his famous statements: "There's no fundamental difference between a living organism and lifeless matter. The complex combination of manifestations of properties so characteristic of life must have arisen in the process of evolution of matter." Now, more and more people began to think about this issue of the physical chemistry of the cytoplasm. They thought about the cytoplasm as this entity they could understand chemistry. And much of this work was then encapsulated in a very famous book, which I recommend anyone to read who's never done. E.B. Wilson had 3 editions in 1920. It was the last. It's called The Cell, The Development of Heredity, and he really summarized all the work of these early cytologists. And when I started my PhD, that field had slumbered since the 1920s, and I remember just how fascinating it was to go to the library, open up this book and see all these amazing questions that they laid out at the turn of the century. That direction of thinking about cells and cytology moved on and carried on in the 30s and the 40s and the 50s, but actually not much progress was made. There was some big attempt to define some of the structures such as microtubules and chromosomes and nuclei, but the field rather became more of a backwater. And that's because it wasn't really possible to make any realistic conclusions about how it worked, turned out, without really knowing molecules. All the theories that were made, very, very speculative, some less speculative, they turned out to be very hard to test experimentally, because you didn't know the molecules, and there was no way to go in and decide if they were right or wrong. Now, at the same time as these guys have been working on these sort of problems of the cell, thinking about the physical chemical point of view, there's another strain of science which is developed, which is really first given by T.H. Morgan, who's the developer of genetics. And I think this phrase, Erich Kandel, is very revealing, that much as Darwin's insights into evolution of animal species first gave coherence to 19th century biology as a descriptive science, Morgan's findings about genes and their location on chromosomes helped transform biology into an experimental science. And Kandel, I think many people saw that Morgan's development of the concept of genetics, if you can define loci genetically, was the beginning of our understanding of how to go about cataloging the genes and loci required for particular processes. And if you just sit down and think, so what we'd like to do then is, the key thing then is to link phenotype to genotype. And that was really what came out of T.H. Morgan's work. He had a phenotype like small wings or white wings, and trying to understand what the genetic basis of that then became an industry where you could say there's a number of different papers that you can pull out along that way. Everybody might have their favorite ones, but for instance, there was the Beadle and Tatum one gene, one enzyme hypothesis. And so that gave the idea that maybe we can find individual genes, we can then find the enzyme. Crick's definition of the triplet code, Sanger the DNA sequence, first molecular cloning loci, and then the key in the 1980s. And so that's really when I started my PhD. People were just beginning to try and clone individual genes required for individual loci. I mean, it's kind of remarkable to think, I'm not a total dinosaur, but when I started my PhD, we didn't know one single gene required for cell division of celiac embryo. Nothing. When I started my PhD, all I did was look at embryos in exactly the same way that Bovary or maybe the microscopes advanced a bit, so maybe Liga in the 60s, and looked at embryos and basically used very similar ideas to try and understand how they were working. But then, the crucial thing were 2 things happened that have then revolutionized this linking of genotype-phenotype. One was the discovery of RNA interference by Farr and Mello, and the other one was the sequencing of the celiac genome by John Salston. And I was actually kind of lucky enough to be in my PhD in the same lab as Andy Farr. Andy Farr, I don't really remember very much about him except that my main goal in life was to try and find if Andy Farr had any vices. Okay, because he just seemed to be somebody who worked in the lab, had no vice. He didn't drink alcohol, didn't drink coffee, didn't have a girlfriend, didn't do sport. He didn't do anything except work in the lab, but then maybe that's what you need to somewhere. Very good was a bit more party, I think. Actually, the thing I remember about Andy Farr was, I one day said, Andy, listen, Andy, you've been in Cambridge, you have never been to a disco. You've got to be a disco. And that's, because you've been all this time, so I said, all right. So he decided to come along. And we go into this disco, and it was really called loud music. And I looked around, and Andy taking his anorak, tied up the hood, and he sort of tied it around. Anyway, so that was the the sort of key in terms of relating genotype phenotype, at least in my opinion. And that's sort of where I came into the story, because I'd known Andy as a PhD student. When you discover discovered that RNA interference, and he told me about it on the telephone, I realized immediately that this was a great moment. Right? That now we could finally, instead of messing around, linking genotype to phenotype in the old way. So when I started my lab, we cloned one gene, or two, that discovered the loci. It took 3 years each. Okay, to do that, 2 students, are basically all they've done for their PhD was to find out which gene corresponds to which altered phenotype. And I realized suddenly that this was a way ahead. And I came to the lab, and I just said, let's see, we're going to, no, that's it. Stop what you're doing. We're going to move over to doing RNAi screening. And I think that's one of the key things that I think is very important to remember that in science. You know, science is a matter of gambling, right? It's not a secure business. It's a business of gambling. And it's very important to come and roll the dice. So that was clearly the first case that really came and rolled the dice and said, that's what we're going to do. But it happened to correspond to the time where we set up the Max Planck Institute, and we had a lot of money for primers and other such nice goodies necessary to do large-scale screening. I remember a few discussions with Kai in the office, because that was the thing that is amazing also to think about. When we set up the institute, there was only small-scale biology. There was no large-scale biology. There was no DNA sequencing. There was no screens. And then the institute got set up, and wham, you know, RNAi was discovered, the human genome was sequenced. You know, so suddenly we had to start working as biologists in this much larger scale. And so, so the experiment we did was, you know, the first genome-wide screens in 2000, together with the lab of Julie Aranger, who did it a different way using a different technology. And basically the goal was very simple at that point, was to say, all right, what are all the genes in the C. elegans genome that are required for cell division? And so here they are, this is some original paper on the C. elegans sequence, and the black lines represent genes. And so we thought, let's take RNA interference, and we'll make double-stranded RNAs, and we'll RNAi each gene, and we'll ask which ones are required for cell division. And what I hoped to get out of that was a catalogue, and a complete catalogue. And why did I think at the time that a catalogue was so important? It's because I've been working in yeast, and I've been working on yeast kinetochores. And we made some isolated kinetochores, and we were trying to work out how they worked, and we were trying to discover which motor was required for the kinetochores. And then, and we having trouble with it, and then along came the sequencing of the yeast genome, and there were 5 kinesins. And I realized at that point that we can make deletions of each one of those 5. If none of them affect kinetochore movement, by definition, motors are not required for kinetochore activity. And so that aspect of completeness, because before these large-scale screens, every time you got something, you'd think, okay, maybe there's another molecule. If I can only find another molecule, maybe I'll make more progress, and I'll make more progress, rather than sitting down to think about the function of the problem itself. And so we started doing these RNAi screens to identify the function of genes, and basically made a genome-wide design of double-stranded RNAs, and we synthesized them, and we microinject them into worms, and then we looked for cell division defects in the embryo. And we did that by video microscopy. And there are a number of things that then came up in that point, which we all face today, which is how do you handle large amounts of microscope data, how do you make large numbers of reagents, and this sort of issue. Now, I think a key thing that came up there was, you know, in order to understand these large data sets, you have to be quantitative. Right? So there was no point, we were not able to, we tried at the beginning, but we were not able to pull this data together simply by going through the old way and saying, yeah, cell division defect, meiosis defect, mitotic defect. That wasn't going to help us. And so we came up with a quantitative way, and I'll just go through that because I think it's one way to think about how to quantify these points. So we divided up the embryo into 47 different things that could go wrong. And if something went wrong, we gave it a 1. And if it didn't go wrong, we gave it a 0. And we repeated the experiment 5 times. And so we got a heat map of defects. So this is one particular gene that has, say, 5 out of 5 embryos had this defect, and 0 out of 5 had this defect. And we're able to put this together into a heat map, and this heat map sort of defined the set of genes required for cell division. Now, you can put this sort of, you know, slipped off the bottom. Okay, sorry, Chris. Thank you, Chris is showing me. Yeah, don't sit down. Yeah, slipped off the bottom. So that's, you know, you can put these categories of genes required for certain processes. But the question is, you can ask them is, how is the function of these 800 genes coordinated? Because in a sense, you know, we've done this cataloging experiment. And then you can think, well, we've got these 800 genes required for cell division. So then came the question of how they are organized. Now, one thing that's, of course, very clear is the cytoplasm is not an undifferentiated soup of genes. So I think one of the most frustrating things in many of these systems biology papers, you see these large numbers of differential equations, is they ignore completely the substructure of the cell. And that's, as biologists, what we absolutely rely on in trying to make sense of this problem. And of course, one of the ways that one makes sense of this problem is by understanding that proteins tend to be large protein complexes. Okay? So molecular machines tend to be protein complexes, such as the ribosome or the nuclear pore complexes. So proteins make these very large sets of protein complexes, which are one way that the cytoplasm is organized. And of course, they even make more complex structures, such as microtubules, okay, which we study in the lab. These are essentially just complex arrangements of tubular molecules, or for instance, centrioles, shown growing here in a nice cartoon done by Francisca, who's actually in the back filming her cartoon. And, so these are the large sort of protein complexes, which we can look at and try and understand how they work. And that, of course, has been part and parcel of the whole development of molecular genetics, has been tools to study the activity of proteins. Right? So at the same time that people were developing tools to the genetics and the genomics of DNA sequencing and the RNAi, of course, all these techniques, such as mass spectrometry, electron tomography, X-ray crystallography, and NMR, were also being developed. And these have got to a very high level of sophistication, allowing us to understand protein complexes, their structure, how they're put together, and how they work. And there's something which I've called, some of these things, which is the Industrial Revolution of genetics. So that, this process of trying to understand the genotype, phenotype, and what proteins do, is the movement of labor from the cottage industry to the factory. And that's exactly, of course, what's happened in the genotype to phenotype movement, which is that instead of doing genotype phenotype analysis in the individual lab, it's now being outsourced to these large genomic centers. And that's one thing which I think is really worth pointing out, which is when that happens, you want to get out of that in small-scale biology. Right? In my opinion, there's absolutely no point in individual labs, especially in high-profile institutes, doing too much of this phenotype and genotype at a small-scale level, because that's all becoming industrialized right now and being taken out of the hands of the small-scale labs. So if you look at then where we are right now, you can say, I think it's sort of summarized in this slide, which is that I talked about this issue of how we link the interaction of individual molecules to the complexity of the cell. And what's happened, of course, is we've defined these catalogs of genes, and we've made some steps to understand how they form protein complexes. And that has really allowed us to understand many aspects of the entomology of the cell, and the way that things are moved around inside cells, and many other aspects of the entomology of how cells work. But, having done all that, you can come back and ask the following question, which is, have we answered the questions posed by E.B. Wilson? So, E.B. Wilson was interested in how the cell is organized into a functional unit, as well he summarized all this data, as many other people were at that time. And of course, the answer is, we have not. We have not at all understood how the cell is organized from the catalog. And it's a little bit like the way I see it as climbing a mountain. You get over one ridge, and you're so happy about that, but then you see the whole peak is in front of you. And I think that's one of the things that we have to remember, which is that the definition of the catalog was an absolute triumph of humanity, like sequencing the genomes, the ability to define what those genes were about. But they haven't actually answered this question of how the cell is organized into a functional unit. And one of the big problems about that is, of course, is that many of the actual structures that E.B. Wilson was interested in, which we ourselves are all interested in, are not obviously protein complexes of the kind that we used to study. Right? So if you look at the scale here, things like centrosomes, kinetochores, protein RNA bodies, nuclear bodies, these all have this tend to be very large structures. And they're large, non-membrane bound compartments that have no obvious structure. And so much of what we're interested in cell biology falls at that level. And yet, we haven't really understood how those are put together, far from understanding how they are coordinated cell. Like there's the questions such as, what controls the timing? Why does everything happen coordinately? Do we understand that? We definitely don't understand that problem. You know, some of the problems we work on in the lab, such as why do a C. elegans embryo grow over a 25-degree range of temperature? You know, how can it adapt the whole range of growth at these different temperatures? We don't understand those problems. You know, we don't understand how the cell knows to make enough of all the different 10,000 proteins required to put it into place. You know, these questions of global organization are things that we just don't understand. And I'd just like to take a little bit of time now to think about these issues of these rather more general, these issues at this level of organization. Think, you know, what can we learn about and think about how they're organized? Because if you look at that level, there's all sorts of interesting things happening, okay? Such as, you know, there are compartments forming, such as the cortex. Here's the C. elegans embryo showing the PAR protein segregating. Or, for instance, you know, we can look at, say, chromosomes and centrosomes going through cell division. And so here's the spindle apparatus setting up. And all of these compartments are large, non-membranous bound organelles. And the question you can ask is, what are the rules to put them together? Now, we can distinguish them because one of the key things they have is no obvious structure. So one of the things that's really bedeviled the whole study of these kind of problems is that if you shine an electron microscope on them, or you try to put them in a structural technique, they have no obvious structure. For those of you who worked on the centrosome all your life, you know that centrosomes, for instance, are called sort of amorphous electron-dense structures, right, with no particular structure. And so that's one of the problems. The second thing about these compartments is they turn over extremely quickly. So one of the defining things about protein complexes, which was very clear, was that protein complexes tend to be rather stable. If you take something like gamma tubulin that we work on, or take a ribosome, you know, you can let ribosomes sit in the bottom of a test tube, and they'll be stable over many, many, many hours, many days. But all these components we're interested in turn over very quickly. But the protein complexes that make up these compartments tend to turn over rather slowly. You need 1 2 hours. But I'll just give you one little example of that shown here, which is, let's take the centrosome. So the centrosome shown here is electron sort of dense fuzzy material surrounding something called the centriole. Now, what you can do is you can label protein compartments which belong to the centrosome with GFP. And so you can label the gamma tubulin compartments with a GFP. And then when you put that inside an embryo, you can then photobleach the embryo and then it'll recover very, very quickly. So this has taken about a couple of minutes. You've basically recovered the fluorescence of the centrosome. And so that is the key conundrum which we all face in cell biology, which is what are the rules which put these complex compartments together? How do they stay together? And are they organized? So we understand that problem for protein complexes because you have stereospecific interactions between different proteins in the complex. Those keep them together. They have faces interact. We can crystallize them. We can study the structure. But these particular larger compartments, we don't really understand very much about how they're put together at all. And what I'd like to just tell you about one little story, which I think shows us what sort of things we can begin to think about in terms of understanding these problems. And that's thinking about the structure called the PICO. Now, the structures I'm talking about are what we call the mesoscale. Okay, so the nanoscale are these structures here, shown as protein complexes. But the mesoscale is this intermediate scale of structures, which is where the sort of state of the art is, as I said, in cell biology, the formation of these structures. One of them, these kind of structures, are protein RNA bodies called P granules. Now, P granules are cytoplasmic hubs of proteins and RNAs, and they are required for the germline in forming C. elegans embryos. Well, I want to just talk to you about this problem because I think it illustrates how there are so many interesting phenomena out there in studying the cell once we get beyond the issue of thinking about individual proteins. So, P granules are interesting because they are complexes of proteins and RNAs, and they have to segregate into the future germline of the embryo. If you look at that here, you can see them segregating to one end of the embryo before division, and they define the future germline. these are really beautiful structures to study. Okay, they've been studied for many, many years. And they are key examples of the kind of structure I'm talking about. Very, very large, a few microns across. And if you photobleach them, they'll turn over very, very quickly. So what are the rules that keep these things together? And so when we started studying this problem, it was the work of Cliff Grandvine, who was in the labs now at Princeton. He looked at this question by studying the fate of individual P granules in the embryo. And what he determined was that individual P granules have very different dynamic properties in the embryo, right? Which is that they tend to shrink at one end of the embryo, and they shrink and they grow again at the other end of the embryo. So what he discovered about P granules is they were very, very dynamic. Now, of course, that's what we tend to discover when we study all these kind of problems, which is you look at them and they're very dynamic. They're turning over very quickly. So the question is, how can they work? And this was where I think that, I sort of had one of the most exciting experiences of my life, which is I always go to Woods Hole to teach for 5 years. And that's a really great time. So I can really recommend anyone here, go to Woods Hole if you want to have a good time, learning about science. Okay, so Woods Hole organizes these courses in cell biology and also physiology and in developmental biology. And it's a great time because you go there for a couple of weeks, you work with somebody on a particular problem. So every 5 years I had 10 students. And we decided 1 year to look at P granules. And we had some sophisticated microscopy, and we thought, let's look at what they look like at high resolution. And when we did that, we made a remarkable discovery, which is P granules, far from being granular in structure, turn out actually to have a liquid-like state. And so what we discovered is, here's a little P granule on a nucleus. And you'll look at these little P granules, and you'll see them coming together and fusing like liquid drops. And then this one here, see it coming together, and they're fusing just like two liquid drops. And that was an absolutely fascinating discovery, because the idea that a cytoplasmic component could be acting like a liquid was very alien to the way we thought about things. Right? We tend to think of that as more kind of like a solid-like fashion. But I'll come back to it in a minute. Because let's have a look at another case of it where what we did is we took the P granules and we squashed them between a slide and cover slip. And now you can see them dripping off the nucleus, a little bit like honey dripping off a spoon in the morning. Okay, so you can see all these dripping off. So that was a sort of amazing discovery for that time, because the more we thought about it, the more we realized is that there's all these features of P granules that suggest they're liquids. First of all, they're spherical, and then they tend to wet when they attach to the nucleus. So you put a bit of glycerol on the slide, it will wet, and they can also fuse into larger spheres. And all these things are very characteristic of something being a liquid. Now, you might ask, why is that interesting? And one first thing to think about is that P granules can be understood by analogy with colloidal liquids. Right? So colloidal liquids are things like cooking, okay? So colloidal chemistry, okay? Which is assemblies of weakly interacting particles in another liquid. But the key thing about, and why it's so interesting is, we know a huge amount about physics of liquids and the chemistry of liquids. And this is beginning to come back to the old work of the 19th century cytologists, people like Alexander Operand, who began to think about these problems in physical chemistry. So the conclusion then is that P granules sort of are liquids, and you can ask, why is that interesting? And the key thing is that liquids have rapid turnover internal contents. Right? So and maybe the best way to describe the difference in a liquid and a solid is like a playground. Right? So if you drop your kid off at school, they will sit in a classroom all day, and that's a bit like the solid-like state. Right? You can always know where your kid is in a classroom. And that's exactly what solid is like. When you look at a protein, the amino acids are always going to be in the same place time after time. And that's why you can do structural biology. Right? Structural biology relies on the fact that all the amino acids are always in the same place when you come back and look at them over and over again. And all the techniques like crystallography, tomography, they all rely on that particular thing. But the problem is that all the standard teachers of structural biology developed for the study of enzymes are no use for understanding the properties of liquid-like structures. So that's why, that's one of the interesting things. The second thing is, of course, the liquids undergo phase transitions. Just to give you an idea of what I mean by phase transition, the most common one you're used to is the idea of water vapor. So water vapor undergoes a phase transition from water vapor to cold. When you decrease the temperature, you get condensation of the liquid onto the cold slide. And so that is a classic form of a phase transition, which is what happen when you breathe out on a cold day. And the reason that's interesting is because phase transitions are ways in which you can get large numbers of molecules in the same place through quite simple rules. Okay, so the reason that things undergo phase transitions is basically you can use quite simple rules to define where they go in one compartment or another. And so, and I think even more sort of exciting for me at the time was that Kai Siemens had been working on lipid bilayers ever since I've been in the field. I must say that for many years I used to sit listening to talks on lipid rafts. You know how much we tease Kai about lipid rafts all the time, completely not understanding at all what he's trying to get at. Okay? And I listened to many talks about it. And I think that's part of the problem, because the idea of the lipid rafts, these phase separations of components into, it's two different phases in the membrane, doesn't make intuitive sense at all if you've spent, like I had, your whole career thinking about individual proteins and genetics and the fact that single individual mutations affect things in individual ways. But in fact, the whole science of genetics has not been very useful to think about membranes. Okay? And that's exactly the point, that when we began to see these things in these sort of liquid-like states of cytoplasm in the mesoscale, that began to really suggest to me, and I finally, first of all, understood what Kai was getting at, and that was clearly my own ignorance and not taking enough time to try and think about it, but also just suggests that these general, very interesting issues of how you organize things in the cytoplasm at large scale, without, in ways that are very non-intuitive for how we think currently about how biology is put together. And so, and I think the interesting thing for me about that is that this is always sort of fascinating about coming back to old studies with new ideas. So what happens to fields is the following. They go for a certain while, and then they tend to just dissipate. And if you look in, the library, as I remember the most sort of salutary experience for me is when I was a postdoc. I decided I was going to go down and make an amino acid oxidase for some obscure reason. I went down to the library at UCSF, and there was this huge array of journal of enzymology, whatever it was. And no one had touched those for 20 years. Like, you picked it up and you blew the dust off. And that was a field that basically died out. In the 60s and 70s, enzymology was absolutely the cutting edge in the Krebs cycle, and then it gradually dissipated because nobody could make any progress. All people could do was isolate enzymes from liver and other things like that, study their properties, and all the papers, if you look at them, have a sadly similar quality to them, which is, we isolated the enzyme, we did a Q10 analysis, we looked at its molecular weight. And for the benefit of hindsight, you can see that all those poor scientists at the time really were not doing anything very fundamental. And so, so I think that and that's what happens to fields. And then it's interesting when you can come back and begin to say, aha, now with the new ways we develop, now we can go back and ask the old questions. And so, coming back to thinking about E.B. Wilson, 1899, right, who said, the granules are liquid in these forms, a conclusion I've confessed surprising result to me, for we're so accustomed in our studies to think of granules as solid bodies, we're apt to forget that sections show only coagulated material, and that's in science. So, did pretty well there. And then, of course, Alexander Oparin, who I brought up before, he outlined a way in which the basic organic chemicals might form into microscopic localized systems of possible recursors of the cell, from which primitive living things could develop. So he was really interested in the question of the origin of life. And what he proposed, and it's amazing to read his book, he's a suspect character, because he supported Lysenko, in the Soviet times, and that's why he's been a bit forgotten. But he was really a brilliant scientist. And he thought that the best way to go from the Miller-Urey experiment sort of results. Right? So the Miller-Urey experiment is the idea that you can create all these little organic molecules by lightning in a soup. The thing that made most sense for the next stage was the formation of phase transitions of organic molecules to separate out. And the more you think about that, the more it makes sense, right? Phase separations are a very easy thing for sets of molecules to do. And so he cited the work done by John Coarcovitz, which are kind of sort of spherical things in cytoplasm, other experimental studies, including his own, in organic chemicals, which in solution may spontaneously form droplets and layers. Operand suggested that different types of these liquid-like structures might have formed in Earth's primordial ocean and be subject to selection process leading eventually to life. Right. So I think that you look at that at the time and you think, how can we ever study that? And bringing you back to what I was talking about early on in my talk, don't forget what I said is these cytologists and early biologists, they define so many problems. Also true in developmental biology. They define so many problems that they couldn't work out what to do. And the competing sort of way of looking at it of T.H. Morgan, which led through all these different steps, the structure of DNA, all the way through to these description of molecules in the genome and what these proteins do. That was done for the reason that people wanted to try and understand, what these individual molecules were actually doing. So now, I feel that if we take a sort of short history of 20th century biology, the first half of the 20th century was we thought about the cytoplasm with no knowledge of molecules. But the second half, the molecular biology came along to catalogue and understand the molecule of the cell, which has been successful and it's been done. But the key thing now we have to do is to take that knowledge back and apply it to think about the problems of physical chemistry of the cytoplasm in this particular case, or one might want to think about it in developing systems in a slightly different way. So, that's the vision that I have in the lab, and just personally, which is that this is the key thing one's trying to do, is there's no point doing much cataloguing. One has to keep doing some cataloguing, but basically the cataloguing has been done. Right? So, what we have to do is understand how these collective interaction molecules leads to feeds back on this physical chemistry of the cytoplasm. And coming back to the title of my talk, which is individuals and collectives, what I've been really getting at is the point that you can look at individual molecules. So, for instance, we can look at proteins and how they form protein complexes, and almost everybody who does biology thinks about that problem. Right? There'll be a protein, how does it form a protein complex? And that's an interesting question of collective behavior, because you're trying to understand how the collective behavior of individual molecules gives rise to protein complexes that do something. But equally important is, for instance, I've been talking about the protein complexes giving rise to compartments. Okay, that's another collective behavior, because you're trying to understand how the collective behavior of all these protein complexes gives rise to a compartment. And the case I talked about, the non-membrane bound compartments, these ideas in liquids are one way to think about that particular problem. Similarly, one might understand how compartments form cells, or cells form tissues. And that is my take, really, on what systems biology is today. Right? Systems biology, we're trying to understand how the interaction of individuals gives rise to collectives. And this is why we have to model. Because you can't do that without theory and modeling. Right? It's impossible to understand how emergent behavior emerges from the interaction of individuals without modeling. Okay? And that's why in Dresden we put such an effort into this problem, which is to try and marry theory to the theory groups in the university and the physics with the biology group to try and put these points together. And I think that one way to think about why there's such a difference between understanding collectives and individuals is to think about the classic thing, I think, of bird migration. Right? So you can understand how an individual bird flaps its wings. We sort of understand that problem. But that doesn't tell you why birds flock together. They make such beautiful shapes. What the interaction between the individual birds with these beautiful flocks and shapes and patterns. And that's exactly the same problem that one's trying to understand in biology, which is we can understand the individual protein complex, but what are the rules by which all those protein complexes pull together to actually form these more interesting structures in my case? But actually, if you look at the more, sort of nuts fun side of it, there's an interest in this question of how cells form tissues. So that's another interesting thing where one's interested in how the collective behavior of all the cells forms tissues. And again, you have to model that problem. You know that what one individual cell does, but you have to model it in order to understand how all the multiple sets of cells form these particular tissues. So that's where we're at. That is the future of biology now, is collectives. It's understanding collective behavior and how it gives rise to patterns we're interested in. And the thing I come back to and say, and this is what I see as really sad about the current state, this is my main beef with the current journals, which is actually, although you would say the cataloguing is done, which you work on collectives, do you see that in the journals? And in fact, the problem still is that a standard title for any paper is gene X is required for process Y. Now you may laugh, but the fact is, you open up any journal and you see that, and I always do that for the students when they come in, and I say, and then I thought, well, what I'll do is I'll open up, and this is I did this blind, right? The last issue of Development of Cell, and I said, let's look at the title and contents. Okay? And when you do that, it's all the same stuff. Non-regulated, so those blown fuse controls wasp, ERK phosphorates NOS3, WIP acts on FGF, these are all just, gene X process Y experiments. And that is what I think, we really have to fight for now, which is, in exactly the same way that when I read those volumes of things in Journal of Enzymology, that people were still publishing papers on individual enzymes when things should be moving on, in the same way we have to fight for this fact that, the cataloging process of individual genes is effectively over as an era. The great work has been done. And the new way to go, the new path of discovery is to put these things into collectives and try and convince, of course, the editors that that's what we want to do and move in that direction. And I think that is why it's such an exciting time also to be in Dresden, because I think Dresden now has put together one uniquely set of people that are really interested in that problem. If you now go back and think about all the scientists working in the different institutes, universities, you'll see that so many of them are actually interested in this issue of collective behavior and how much of it we have helping us with working together with theory people such as Frank Luliker and other theorists who are helping us trying to understand that particular problem. And that's one of the reasons that we put together this new Center of Systems Biology, which we built hopefully in the car park of our institute. The whole point we're trying to do there is to try and understand the issue of how individuals form collectives. Thank you.
They started off very simply, and then they had to obey these laws. And that, I think, is collective, so you understand what's behind it. What's it granted? All these things behaving in the same way. Even if there are 100 components, or 200, or 300 in there, it's mind-blowing. And most people cannot get it.
I think the most frustrating thing about biology is how myopic biologists tend to be, because these issues that Kai's talking about, which you always run into, how can you have 100? Phase transition, well, water is complicated, but let's say chloroform alcohol trap you do in the lab, right? All the alcohols go with the water layer. And you can say, well, that's the rule there, it's because they have a hydroxyl group. And people say, well, that's fine, but what about if you've got 100 proteins, how does that work? But all you have to do is go to the chemistry department and say, they say, of course, it's no problem. That's easy. We can do anything you want that way. Phase transitions can be set up in any big direction. So I think, the key thing that we have to do as biologists is to move out into physics and into biology, into chemistry, and understand what they can add to this particular problem. Because normally it's like 100 years of theory, which you can easily apply to a problem. There's one other thing I want to bring up here, which is there's a very good article I recommend by this guy. So this idea of that biologists, we tend to instinctively put things into these hierarchies of organization. That's an old concept as well, which was first enunciated by this guy Hyman in '62 in the Architecture of Complexity, where he made the point that all complex systems can have a one-with-one hierarchy of all of them. And that's something which I think is an interesting way to think about this problem.
According to this, so do you think it could be same rules who are applied in a tissue environment to put each cell together and collect it are the rules who bring birds or fish together to form big swarms? So is it in a 3D environment the same?
Not exactly, but of course the physics. So that's a very interesting point, which is, can you use the same rules at these different scales? And of course, we use different rules at different scales and different theory. The theory of how you define an atom, let's say at a quantum mechanical level, is very different than how you talk about pressure on a piston. Okay, you'll use different kinds of physics to describe those two different things. So of course there'll be different ways of theory to think about. On the other hand, a lot of it does get down to certain things like statistical physics. Statistical physics can be used to describe the stock market or birds flying, or can be used to describe molecules in the cell. So there are sort of physical principles behind them that are similar.
So is there yet a cholesterol of peak values? Basically, are they formed by using, let's say, one structural component or something like this, or is it really the collective of the hundreds of molecules that sit on there?
Yeah, we don't know that, and I think it's one of the interesting questions about these things is, if you think in cooking, right, where everything comes together into this big sort of mixture, there's no one thing that seeds it. The question, I think, in biology will turn out to be, are there individual things that form the core structure, or do they simply form a phase spontaneously? My bet will be there are probably a few proteins that make the sort of phase initially, and then other things segregate into it. But that's an interesting question for the future.
So, really fundamental problem here that probably you weren't really buying into this big problem, but that is the emergence of order and complexity. And where does it come from? It's in complete defiance of the second law of thermodynamics.
Yeah, I agree completely with that. I mean, and that's...
You talk to the physicists, they describe this as a Boltzmann fluctuation.
Exactly. Boltzmann
And
fluctuation.
life on Earth
Yeah.
is in defiance of the second law of thermodynamics. But
One of the laws.
It's not in defiance of the second law,
it is.
which applies to isolated system.
Yeah, this is what the physicists say. They say it doesn't defy the second law because you are defining the system that you're looking at incorrectly. And if you define the system you're looking at as, say, the whole universe, then the entropy is increasing.
I think one of the things is...
We're a fluctuation that's the exception. But I think that's just ludicrous. It's like invoking God to explain life.
I think maybe let's think of it a slightly simpler way, which is that I think the thing the reason that physicists are so interested in biology is because it is not dead, it's alive. It uses ATP hydrolysis to do interesting things, energy flux for the system. So a lot of physics describe equilibrium systems, but everything you work on is out of equilibrium. So I think that's a lot of the stuff that physicists have used to describe things isn't very applicable to lots of biology for that reason.
Yeah, but how did it emerge?
Well, I think
there's
you
no
could-
explanation.
We know things will tend to, phase transitions will tend to just happen with molecules like each other, fate will tend to separate alike and unlike. And I think, so that's why I like this phase transition idea. You don't need anything special to start off with these sub-organizational structures. And then within that, you can start, I think what happens is that then within that, the interactions then get tighter and tighter and tighter, so you end up with more and more, more and more defined structures. Now that's why phase trans is very helpful for you to think about that problem.
It's often techniques or tools that are really driving a
Yes.
field forward, or something like RNAi.
Yes,
Kind of
yes.
something. Do you think there's any technique at the moment that might drive biology in the direction that we wanted to, or at least that is?
Well, I think the key step forward in our particular system will be going back to biochemistry. Is the way I see it. Okay, so I think the big problem we've had is that we've got away from biochemistry, and these problems can only really be solved by going back to the test tube idea and really looking at techniques to study rapid interactions. So because most of the techniques we've studied so far are stable interactions. So what we have to do is develop techniques which isolate very, very transient interactions, which gives some sort of readout when you get a transient interaction. And that can really only be done, I believe, in a test tube by looking at those particular issues. So I think that's it's not a new technique, but in fact, biochemistry hasn't gone very far in the last 50 years. We still use the same columns I used as a student, Cephalodex, whatever, mono-Q, mono-S. I still see the same columns in the drawer. They don't actually use them myself. Actually, well, I'm not sure we use them, but I think they're still there. They're still there. And I don't notice great change in biochemistry. So I think techniques to really isolate, track, and study functional proteins is a key out.
It's very interesting standpoint. Just a question. Do you think we made a new set of measurable parameters to describe collective behavior? I mean, maybe the things we measure right now is not proper.
Yes, I mean, I completely agree with that. We have to understand that the problem we have is the same in membranes. And why has it been so hard? Now I understood finally why it's so hard to make progress in membranes. It's because the tools aren't there. How is it you look at this transient interaction of lipids and proteins in the membrane? We have no ways to get at it. So it's a matter of defining those sets of transient interactions, how quick they are, how long they are, what effects they have on the protein. And that's a big problem, because there's no obvious ways that we can do that.
So you said one of the challenges is to continue the journals. This new biology is one topic change. So I wonder how you're going to achieve this.
Okay, well, I'll tell you a story about that. So, when I was a graduate student, actually, maybe I'll tell you two stories about that. So, when I was a graduate student, yeah. No, okay, let me answer that question first, okay? Okay, well, finish your question.
Well, I mean, okay, you probably know the question, but there is way more data coming up, so the data is starting to way more to deal with the data. And it's much easier to tell a story about nothing.
Okay, let me
tell a story about nothing.
Yeah, so let me, exactly, so that's the point. So the three questions, first of all, so I'll start by Sidney Brenner. So I had the great luck to be a PhD student with Sidney Brenner, who, for those who don't know him, he worked out the triplet code, and then he went on to start C. elegans single-handedly, and then he really got the sort of sequencing efforts going. And so, well, actually my first interaction with Sidney Brenner was, I'd arrived to my PhD, and I was 21, and Sidney Brenner asked me after a couple of weeks to go up and have lunch with him. I was really excited about this, of course, the head of the lab, asked the student to go up, head of the institute at that point. And my direct boss is a guy called Mark Bretcher, who's head of the division. And I went up and we sat down. He said, Tony, he ate his carrots, and he said, Tony, you know what my biggest mistake was? Did you ever make mistakes? I don't know. Yeah. Hiring Mark Bretcher as head of your program. So there I was a great student. Anyway, so then I thought I'd better sort of change the topic. And I said, so Sidney, tell me about JMB, Journal of Molecular Biology, because I know he'd been a founding editor. He said, Tony, do you know why we founded JMB, which is the Journal of Molecular Biology, which now is not what you call one of the high-profile journals, but was the key journal that published most of the beginning work in molecular biology, not Nature or anything. And he said, we started JMB because Journal of Biological Chemistry would not publish any papers on DNA. Okay? They wouldn't publish molecular biology papers. There was a whole set of people lost in biochemistry at that time who didn't see molecular biology as an interesting field, and that's why I always say no one ever listens to me, which is you've got to start a new journal, because it's impossible in the current journals to do anything, and that's why breaking the stranglehold of cell nature is such essential for the future at this point, because the editors are always 7 to 8 years out of date, right? The editors in these journals, they trained at the time for the early fallback collective behavior, so how can they possibly understand that's interesting, because they've had no training on it. So that's, I think, the key thing is starting new journals. And the other thing which I'd say is that I think we're in intermediate time, but I think in the future, maybe a bit like information technology, right? Nobody's really interested in building computers. They're just interested in the information coming out of it. And I think the key thing we see that now is with DNA sequencing, right? You don't get a paper for publishing DNA anymore, you get a paper for bioinformatics. So I think we're kind of this intermediate time, especially the things that you're interested in, where it's not quite there yet, but pretty soon we'll be there, where it's the analysis, the meta-analysis of the data, which will be interesting, not the data itself.